Recently in one of my weekly live streams, which I'm doing every Monday night at 5 o'clock Pacific, 8 o'clock Eastern, I talked about the differences between an integration by parts problem for definite integrals versus indefinite integrals. And I wanted to dive a little bit deeper into how to apply the integration by parts formula for definite integrals. So in this video, I'm going to be showing you exactly what that formula is and how you can apply it in order to do integration by parts on a definite integral. So by the end of this video, you should be a lot more comfortable with integration by parts on definite integrals. If that sounds good, be sure to stick around to the end of the video. And without further ado, let's jump right into it. So now we're going to get into some examples of what it looks like to do integration by parts for a definite integral. So this is going to be very similar to what we just did in the last problem. In other words, very similar to using the integration by parts to find the integral of an indefinite integral, with just kind of one small kind of edit to the formula. And this formula is also on my integral calculus cheat sheet, or my calculus 2 study guide. Very similar formula with one main difference. So basically, what that formula tells us is if we have the integral from a to b of u times dv, this can be rewritten as u times v evaluated from a to b minus the integral from a to b of v du. So very similar formula. All we're really doing is just kind of evaluating between these bounds is really kind of the main difference. So again, same process that we normally want to do with integration by parts. First thing we need to do is figure out what we're going to make our u, what we're going to make our dv, then figure out what we're going to make, or what our du is based on the u we chose in the first step, and figure out v based on the dv we chose previously. So in this case, we can see that we have a dy over here. That tells us that y is our variable. That's kind of an unusual variable. Usually y represents a function, but in this case, since the dy is here, that indicator tells us y is your variable. We're integrating with respect to y. So when we're looking at this, again, what do we want to take the derivative of? What do we want to take the antiderivative of? Well, before we do that, what I'm going to suggest is we need to kind of rewrite this in another form that makes integration by parts actually make sense. Because integration by parts requires that we have the product of two things, u times dv. Well, here we have a quotient, we have division instead of multiplication. However, what we can actually do is we can rewrite this function, ln of y divided by square root of y. First of all, we can rewrite square root of y. So that's the first change I would suggest, is don't think of square root of y as the square root of y. Think of it as y to the 1/2 power. Because y to the 1/2 power is exactly the same as square root of y, right? Taking the second root is the same as raising something to the 1/2 power. In general, if you have an nth root of something, you can rewrite it as that thing to the 1/n power. That's always going to be the case. So in this case, that gives us y to the 1/2. Well, what you also want to consider is that, or when you have a power, something raised up to a power on a denominator like this, you can move it up to the numerator by making the power negative. So ln of y divided by y to the positive 1/2 power is the same as ln of y times y to the negative 1/2 power. By making the power negative, we can move it up out of the denominator of the fraction, which is convenient because now we actually do have the product of two things. So now we can actually apply this integration by parts formula. So to do that, what we need to do is, again, decide what's going to be our u, what's going to be our dv. Well, our u is generally the thing that's going to cause us, be easier to take the derivative of, or create a cleaner thing to take the derivative of. And dv is the thing that's going to create a cleaner thing to take the antiderivative of. Very similar to the last example we did, y raised up to some power is not going to really matter whether we take the derivative or the antiderivative. In either case, we're just going to apply power rule, and we're just going to end up with some constant times our variable raised up to some constant power. In either case, whether we take the derivative or the antiderivative. However, ln of y is going to be much, much better to take the derivative of than it is to take the antiderivative of. Because the derivative of ln of y, or ln of whatever you're taking the natural log of, is just 1 over that thing. So the du in these integration by parts problems is always just going to be the derivative of u. Well, if u is ln of y, du is just 1 over y. Okay. If ln of y is our u, then y, and actually I should have had a dy on here as well, y to the negative 1/2 dy is going to be our dv. So the dy is always going to carry in with the dv here, and then we also need a dy in our du term. So the du term and the dv term are always going to have dy, or d whatever your variable is. So then once we've decided that y to the negative 1/2 is dv, we need to find v by taking the antiderivative of y to the negative 1/2, or take the antiderivative of dv. Well, like I said, to take the antiderivative of y raised up to some constant power, we can just use the power rule. Power rule says we're going to keep our base the same, keep our base as y, raise our power by 1, or add 1 to our power. Negative 1/2 plus 1 is the same as negative 1/2 plus 2/2, right? We need to get a like denominator to add fractions. Negative 1/2 plus 2/2 is positive 1/2. So our new power is going to be positive 1/2. And then, by the power rule for integration, we have to, after we raise our power by 1, we have to divide by our new power. Dividing by 1/2 is the same as multiplying by the reciprocal of 1/2, which is 2. That's going to give us 2 times y to the 1/2. Okay, so now once we've found these 4 pieces here, we can plug those 4 pieces into our integration by parts formula. So we're going to get the integral from, a to b, 4 to 9 in this case, of u times dv, which we've said ln of y is u, y to the negative 1/2 is dv. We can rewrite this as the integral, or I'm sorry, u times v, so ln of y times 2y to the 1/2, evaluated from a to b, so from 4 to 9, minus the integral from 4 to 9 of v times du, which is 2y to the 1/2 times 1 over y. And then dy needs to be on there as well. Okay, so now what we've done is we've converted this original integral into one that should be easier to integrate. Before we do that, though, we probably want to simplify this. And that's a lot of times how these integration by parts problems are going to go, is reapplying this integration by parts formula to rewrite our original integral as another one. It's generally still going to be the product of 2 things, because that's what the formula says, right? It's just v times du instead of u times dv. But the hope is that the product of these 2 things can actually simplify. A lot of times that'll be in the form of something canceling, which in this case, let's think about how this could cancel or simplify. Having y to the 1/2 and then having a y on the denominator here, these 2 things are going to partially cancel out with each other. Y to the 1/2 divided by y, how that's going to cancel is it's going to basically subtract 1, because y is the same as y to the 1 power. It's going to subtract 1 from this power, right? If you have 2 terms, like let's say x to the a over x to the b, that would simplify to x to the a minus b. So in this case, since we have y to the 1/2 divided by y to the 1, that's going to simplify into y to the 1/2 minus 1, which is going to be y to the negative 1/2. And then we have this 2 out here. Well, if we have a constant multiplied by all the stuff we're integrating, we can pull the constant out of the integral. So the only thing we're integrating now is y to the negative 1/2 dy. We can pull our constant 2 out. The rest of this is going to stay exactly the same. And we're still going to evaluate this from 4 to 9. Okay, so now let's deal with this integral. All we're doing now is integrating y to the negative 1/2. Well, we already did that, actually. If you look back here, our dv was y to the negative 1/2 dy. So to integrate that, we found that it was 2 times y to the positive 1/2. So we actually know right off the bat, this is just 2y to the 1/2. And we do still have this 2 out here, right? It was 2 times that integral. We know the integral itself is equal to 2y to the 1/2. So we're going to have 2 times 2y to the positive 1/2. That's going to be minus. All this is going to stay the same. And now let's think about this. So here, this kind of vertical bar with 4 and 9 written here, all that's saying is evaluate this expression from 4 to 9. Well, what we're also going to have to do, thanks to the bounds of this integral, is evaluate this expression from 4 to 9. So basically what we're doing is we're evaluating the entire thing from 4 to 9. You could do them separately and then subtract them, or you could do them all together. It's really not going to make a difference. You're going to end up with the same number either way. But all that means to evaluate something from 4 to 9, from a lower bound to an upper bound, is you're going to plug in 9 into wherever you see a y. So we're going to get basically ln of 9 times 2 times 9 to the 1/2. 9 to the 1/2 is the same as the square root of 9. So the square root of 9 is 3. 2 times 3 is 6. So ln of 9 times 6 minus 2 times 2 is 4. 9 to the 1/2 is the square root of 9, which is 3. So 2 times 2 times 3 is 12. Okay, so this is what we got from plugging in 9, basically. All we did is just go to wherever we see a y, which is here, here, and here, and replace it with a 9. And doing that leaves us with ln of 9 times 6, all minus 12. Okay, then we need to minus whatever we get from plugging in 4 into all of our y's. So now go to all of our y's here and replace it with a 4. And then we're going to do basically all this from plugging in 9, all this from plugging in 4. It is very important that you need to make sure you put parentheses around your two pieces like that. And then once you figure out what the value of what's inside the parentheses here is, then you can deal with the fact that you're subtracting them. So now if we plug in 4 for all of our y's, we're going to get ln of 4 right here. 4 to the 1/2 is the same as square root of 4, which is 2. 2 times this 2 is 4, minus 2 times 2 times the square root of 4, which is 2. So 2 times 2 times 2 is 8. Okay, so then we can simplify this. We would have 6 times natural log of 9 minus 12. This negative sign is going to distribute through the parentheses here. So we're going to get minus 4 natural log of 4 minus negative 8, which the negative and the negative will cancel, giving us plus 8. Then to simplify this a bit further, 6 natural log of 9 minus our 4 natural log of 4 over here, minus 12 plus 8 would be minus 4. And that should be about it. We could probably apply some log properties if we really wanted to simplify this further, but I think this is a perfectly fine answer. This will give us, you could just basically plug this into a calculator from this point fairly easily, or if you want to leave it in exact form, that is a perfectly sufficient answer. I hope you found that video helpful. If you did, please do me a huge favor and hit that like button down below. That's a huge help to me and my channel so I can keep making more videos like this and keep helping you learn calculus throughout the year. And like I said, this definite integral integration by parts formula is on my Calculus 2 study guide. There is a link down in the description below if you want to go check that out. And if you want to keep learning about integrals, I've made several other videos about them. Just go ahead and click on one of those over there and keep on learning. Thanks, and see you next time.